In this video, we're going to review reduction of carbonyl compounds. Let's first define quickly reduction and oxidation in organic chemistry. Reduction refers to gain of electrons or formation of carbon-hydrogen bonds, and oxidation is just the opposite. It's the loss of electrons, loss of carbon-hydrogen bonds, which is equivalent to formation of carbon-oxygen bonds. We're not going to go into the details of reduction and oxidation, so make sure you review it before you continue watching this video if you're not really sure about reduction and oxidation. So let's talk specifically about reduction of carbonyl compounds, and here is the general reaction where this hydrogen represents a reducing agent. So let me just write that here. This is our reducing agent. And if we look at the definition, it was reduction, gain of electrons, or formation of carbon-hydrogen bonds. Here, well, we're going to ignore the R groups. We have two carbon-oxygen double bond, and if we look at the product, we now have one carbon-hydrogen bond and one carbon-oxygen bond. So we formed one carbon-hydrogen bond, and this is what we mean by reduction. Here are some of the reducing agents that you will probably encounter: sodium borohydride, lithium aluminum hydride, lithium borohydride, and borane. Sodium borohydride is the weaker one, and it can only be used to reduce aldehydes and ketones. So reduces aldehydes or ketones. Lithium aluminum hydride is the stronger one, and it can reduce aldehydes, ketones, esters, carboxylic acids, and even amides. Lithium borohydride can reduce aldehydes and ketones. And it can also reduce esters. Borane is usually used to reduce amides or two, and carboxylic acids. Okay, we're going to start with sodium borohydride. So sodium borohydride is a salt, and this is the borohydride part. So the boron is attached to 4 hydrogens. It's negatively charged, and sodium. So these are hydride ions. And we know hydride ion is negatively charged, and that's why this is a strong nucleophile and a base. So we're going to start with aldehyde and ketone. So here I'm showing an example of aldehyde, but this can you can also imagine the same thing for ketone. Surprisingly, the mechanism is not like 100% known, but here is how you can think of it. In the first step, the hydride ion, we said that this is our nucleophile. So if this is our nucleophile, where is our electrophile? Just take a few seconds and identify the electrophile. Yeah, so the electrophile is the carbonyl carbon right here. So again, remember that oxygen is electronegative. It's going to pull electrons towards itself, leaving a partial positive charge here. Or you can also think of it as a resonance structure, where oxygen is negatively charged and the carbon is positively charged. So here's the resonance structure. In the first step then, our nucleophile is going to attack the electrophilic center, and because we can't have 5 bonds, we're going to break this pi bond and we form this tetrahedral intermediate right here. Now in the second step, all we're doing is using acid quench, so hydrogen plus, and what we're doing is to protonate that oxygen to give us alcohol. And you can see that this is a primary alcohol. So starting from aldehyde, we get primary alcohol if we reduce it. Now, what do you think we'll get if we start with ketone? What type of alcohol we get? Just take a few seconds or pause the video and draw the mechanism to see if you can come up with the product. So the product for ketone is going to be a secondary alcohol, because now we have 2 R groups attached to it. This is a secondary alcohol. Okay, so aldehydes and ketones, we can use sodium borohydride. It's a pretty safe reagent to work with, and we get primary and secondary alcohol respectively. Okay, so now let's move on to ester. For esters, we can't use sodium borohydride because it's too weak, and we have to use lithium aluminum hydride. So in the first step, again, you can think of as having a hydride ion as the nucleophile, and this is going to attack the electrophilic center. Again, we cannot have 5 bonds, so we're going to break that bond, and this gives us our tetrahedral intermediate right here. Now we have an oxygen that's negatively charged. You can think of it this way, or lithium can actually bind to it to stabilize it, and this is another structure that you can think of it. Yeah, it depends on the course that you're taking and the mechanism that your instructor is showing. Both of them are correct. So in the second step, we're just going to form our double bond and kick this as this leaving group to get aldehyde. So this is our aldehyde. Now, because we're using lithium aluminum hydride and we know that it's a very strong reducing agent, we can't stop at the aldehyde step, so the reaction doesn't stop here, and we're actually going to do another reduction. So we have hydride ion floating around in the solution, and they're going to attack the electrophilic center again, and we're going to get this intermediate right here. So this is our second tetrahedral intermediate. Now the next step again depends on the course and the mechanism you're being shown. Lithium can exchange with aluminum hydride, so now the oxygen is actually bonded to aluminum hydride, and in the second step we do acid quench. So second step is just acid quench, and that cleaves this oxygen aluminum hydride, and it protonates the oxygen to give us the alcohol. So now we have a primary alcohol. So it's very important to know that the acid quench is actually done in the second step when the lithium aluminum hydride job is done, because remember this is acid, and we know the hydride ion is strongly basic. So if we add the acid with lithium aluminum hydride, the hydride is just going to react with our acidic proton, because acid-base reactions are very fast, and it just destroys our reducing agent. Okay, so let's quickly review. Started off with ester. We use lithium aluminum hydride as a stronger reducing reagent. We reduce it once to get aldehyde, but it doesn't stop there. and we're going to reduce it one more time to get primary alcohol. So lithium aluminum hydride is actually a nasty reagent to work with. It can cause fire when it comes in contact with water, or it can also decompose explosively when heated above 120 degrees. So in real life, for esters, you could use the milder version, which is lithium borohydride in ethanol, so that you don't have to work with this nasty reagent. The mechanism is still the same, so the hydride ion acts as the nucleophile. Now, what if you want to stop the reaction at the aldehyde stage? Well, there's another reagent called DBAL. This is called diisobutyl aluminum hydride. You can use this to reduce esters. It actually stops the reaction on aldehyde, though it's not always the case. It depends on the on your starting material. But there are some starting materials that would stop at the aldehyde if you use this reagent. Okay, so now let's talk about amides. Again, we're going to use lithium aluminum hydride. Our nucleophile is going to attack the electrophilic center. We're going to break that bond, and again, because it's going to be negatively charged, or it can be shown as bonded to lithium, then hydrogen and Nr2. And again, this is just going to, the lithium is going to exchange with aluminum hydride to give us this intermediate right here. Now, the Nr2 minus is not a good leaving group. So this is not a good leaving group. So the oxygen, the electrons on the oxygen are not going to push out Nr2 minus because it's not a good leaving group. Instead, the electrons on the nitrogen are going to make a double bond and kick this oxygen out to give us this imine right here. Now, in the last step, we're going to have hydride again as the nucleophile. It's going to react here, break this bond to make this nitrogen neutral, and this gives us our amine. So starting from amides using lithium aluminum hydride, we can reduce it to amines. And lastly, let's talk about carboxylic acids. Again, first let's look at lithium aluminum hydride. So I mentioned that hydride ions are strong bases. What do you know about this hydrogen? So this is an acidic hydrogen. Remember, carboxylic acids are acidic. So this hydrogen is going to react with this hydride ion, and this gives us the carboxylate ion plus hydrogen gas. Now, in the second step, the hydride is going to attack the electrophilic center. We break that bond, and we get our tetrahedral intermediate right here. And then the electrons on this oxygen are going to make a double bond, kick this oxygen out, and we'll get our aldehyde. Now again, because we're using lithium aluminum hydride, the reaction doesn't stop here. We're going to do one more step of reduction. This attacks here, break that bond, and this gives us our alcohol, primary alcohol. So remember, the second step is just to protonate that negatively oxygen. I'm not showing it because it's just a repetition from previous ones. But there is that second step where you protonate that oxygen. So another reagent used for carboxylic acid is actually borane. And the borane forms a triacylborate with carboxylic acid. So this is the intermediate. And the second step is very fast. This gives us our primary alcohol. I'm not going to go into the details of this reaction mechanism because for intro chemistry, you most likely won't need to know it. But know that borane is also a highly chemoselective reagent for the reduction of carboxylic acids in the presence of other functional groups such as esters and ketones. Okay, so let's just quickly review. We talked about reduction and oxidation. Reduction is gain of electrons, formation of carbon-hydrogen bonds. Here are some of the common reducing agents you might encounter. We talked about reduction of aldehydes and ketones using sodium borohydride. So aldehydes give primary alcohols, ketones give secondary alcohols. We talked about reduction of esters. For esters, you have to use lithium aluminum hydride as the stronger reducing agent. The intermediate is aldehyde, but the reaction doesn't stop there. You do one more step of reduction to get primary alcohol. Amide, the same thing, lithium aluminum hydride. The intermediate is imine, and you do one more step of reduction to get amine. And carboxylic acid, again, lithium aluminum hydride could be used. The intermediate is aldehyde. The reaction doesn't stop there and does one more step of reduction to give primary alcohols. But the better reducing reagent for carboxylic acids are actually borane. Thank you for watching.